for the really fun part. We just saw that P2, in the last video that is, that P2 of 0, 1 is a vector space. Of course, I didn't go through the full proof, but, it's good enough for our purposes. So it is a vector space. And, you showed that it has a basis. In particular, the basis has 3 vectors in it. The vectors are the polynomial functions x squared, x, and the constant polynomial 1. So, one thing we saw last time, right, from this basis theoretic idea, is that the dimension of this thing is 3 because it has a basis which has exactly 3 vectors in the basis. And this is how you define the dimension of a vector space. Alright, so the dimension is 3. That's just sort of a fun side note. And now the thing I want to do is really, the big idea here is that I want to put an inner product on this thing. Okay, so an inner product is really just a sort of generalized idea of a dot product. Okay, so we know how to do dot products, right? We can do that. We've been doing that the entire semester. So what we want to do is just come up with a generalization of that. All right, so this thing right here, this is just a fun side note. Oops. So now the really important thing. Remember the idea behind the dot product. At least as far as the mechanics go. Alright, the idea behind the dot product was that if you are dotting, ABC with UVW, right, just making up names for the vectors here. This is AU plus BV plus CW. Alright, so you multiply component-wise, right, multiply component-wise, and add. So, we are going to use that exact same idea here. Alright, so now we're going to take P and Q, which are both in P2 of 0, 1. Right, in other words, this means that P of x is some polynomial, ax squared plus bx plus c. Q of x is some different polynomial, ux squared plus vx plus w. Alright, so they're both polynomials of degree 2 or less. And what we want to do is think about what this idea could mean, right? This idea right here. Multiply components and add. Because that's going to be our generalization of the dot product. So, the weird thing now is that we want to think of the components of a function. Basically, we want to think of a function as a vector which has infinitely many components. Alright, so what I mean by that is you want to think of the components of a function as what they're doing to individual points. Right, as point-wise evaluation. Alright, so what I mean by that is, P of 0 is a component of P. P of 1/2 is another component of P. P of, 1 over pi is another component of P. Right? All these different values, when you plug in different values of x, these are all going to be the different components of the vector that is the polynomial p. Right, just like up here, you could really think of like component 1 being A, component 2 being B, component 3 being C for this first vector. All right, so it's like if you had this vector, you could plug in the number 1 and it would output the component A. You could plug in the number 2 and it would output the component B. You could plug in the number 3 and it would output the component C, and so on. All right, so this is really the idea of how we want to think about the components of these polynomials, which we're thinking of as vectors. And so what this is going to do for us, right, the first thing we do in our dot product is multiply components. So if we multiply components of P and Q, we will get P of x times Q of x. Right? Evaluate them both at whatever point x, and then multiply them together. And this is going to be true for any x in between 0 and 1. Right? We would, if we wanted to multiply every single component of them together, we would have to multiply infinitely many things together. Right? We'd have to multiply, two things infinitely many times. Right? We have to evaluate P of 0 times Q of 0, and P of 1 times Q of 1, and P of 1/9 times Q of 1/9, and so on for infinitely many values. And which you can just write simply as P of x times Q of x. And then, the interesting part, now we have to add them together. But we've got infinitely many values, as I just said, that we would have to add together. So, we've already seen examples, ever since Calc 1, you've seen examples of basically fancy ways to add together values of functions. And when you are, sort of fancy adding together infinitely many values of functions, well, that turns into an integral. Right? Integration is fancy adding. Right? So this is the analogy here. This right here is your multiplication component-wise, and the integral is adding them together. It's just fancy adding because it's an integral and not a regular old sum. Alright, so this is an important thing for us. I'm going to call this a definition. We define an inner product which is denoted using angled brackets, denoted by on P2 of 0, 1. Oh, also, this is why I specifically chose a small interval for the polynomial space. It's so that we could have nice bounds on our integral here. Alright, so we define this inner product denoted by the funny angle brackets on P2 by the inner product of P and Q is defined to be the integral from 0 to 1 of P of x times Q of x dx. Alright, so this thing takes in, right, the first thing I want you to realize is that this thing takes in two vectors, which just happen to be polynomials because that's the space that we're living in right now. And it multiplies them together to make a new polynomial of degree 2 or less. And then it integrates. And so notice that this is going to return a scalar value. this end result will be scalar, which is exactly what we need from a dot product, or in this case, an inner product. It's just a fancy term that we give to things that aren't the standard dot product. Alright, so this thing takes in two vectors, and it returns a scalar, just like we want it to. So, let's check something out. Is the basis that we defined before an orthogonal basis? Right, now we've got an idea of something that is like the dot product, and so we have this idea of orthogonality, right? If we're in Rn, u dot v equals 0 if and only if u is orthogonal to v. And so what we can do now, if we're in P2, we now define orthogonality via the dot product, or rather the inner product. Alright, so we say P is orthogonal to Q if their inner product is 0. Alright, so this is the only sort of subtle difference now. Instead of observing, because we have vectors in front of us that we can look at, like in R2 or R3, instead of observing that the dot product, the way it's defined, happens to return 0 when the vectors are perpendicular to one another, well, now we can't exactly observe when polynomials are orthogonal, because what in the world does that mean? So what we have to do instead is define orthogonality this way. Alright, so one thing that we can check with the spirit of the other basis videos in mind is whether or not this basis, let me call it B, is this basis, which consists of x squared, x, and 1, is this an orthogonal basis? Alright, perfectly natural question to ask now that we have all of these ideas under our belts. And so to check this, all we need to do is just start considering their inner products and see if we get 0. Alright, so let's consider the inner product of x and 1. For example, this is going to be the integral from 0 to 1 of x times 1 dx. This is the integral from 0 to 1 of x dx, which is 1/2 x squared from 0 to 1, which is 1/2. Notice that this is not 0. Right? Therefore, 1 and x, the polynomial 1 and the polynomial x, are not orthogonal. Okay, so these are not orthogonal. Okay, so this leads to so many questions. Are there polynomials which are orthogonal to one another? Right? Do they even exist? That's a question. So, can we find polynomials which are orthogonal to one another? This is a question. Another question. Remember that we had what I called the cosine theorem. Which stated loosely that u dot v in Rn is equal to the magnitude of u, magnitude v, times the cosine of the angle between them. So we have this theorem, again, this is an observable theorem in Rn. So in R2 or R3, you can physically look at the vectors in question. You can get out a compass or a protractor, and you can measure the angle between them. And it just happens to obey this formula. Well, now that we are in a polynomial space, it is not as straightforward as just saying, get out your protractor or get out your compass and measure the angles between things, right? What does that even mean? And let me give you basically where this question is going. It's inspired by question 1 up here. The orthogonality question is asking if we can find two polynomials which are pi over 2, whatever the angle between them is, they should be angle pi over 2 between one another. In other words, they should be orthogonal. And so a more refined question: can we define the angle? Let me put it in quotes, because what does this mean? Between polynomials. So the answer is yes, but we have to be very careful about how we do it. So the first thing we want to do is address this part of the cosine theorem. What exactly does the magnitude of a polynomial look like? All right, so how do we define? The magnitude of a polynomial. And again, this is for p in this set of quadratics on the unit interval. All right, so how do we define this magnitude? Well, if you recall, in Rn, right, we looked at u dot u, and this is just regular old vectors, regular old dot product. This turns into magnitude u squared. Right, this is one of the nice properties of the dot product. So, rewriting this, the magnitude of u should then be equal to, the square root of u dot u. All right, so this is all in Rn. So, again, just like, sort of inspired by the previous ideas of how we would define orthogonality using the dot product or the inner product on P2, we are now going to define this is going to be called the 2 norm on P2. And we define it as the following. The notation is a norm with a subscript of 2, and it is defined to be the square root of the inner product of P with itself. Right, and it's called the 2 norm, and that's how you know that's why there's a 2 down there. It's because it's called the 2 norm. Now, the reason why it's called the 2 norm comes from the fact that if we expand this, right, what does this actually look like? So again, P is in P2, meaning that P is a function. Right? It's in particular a polynomial, but it's a function. And so the inner product of P with itself looks like the integral from 0 to 1 of P times P dx. In other words, this is the integral from 0 to 1 of P of x squared dx. And so this idea here is that the magnitude, the 2 norm, it's the magnitude of P and the 2 norm, this is the integral from 0 to 1. Let me write this a little more carefully. P of x squared dx. And then it's under a square root, which I'm going to rewrite as a 1/2 power. All right, and so the fact that this thing is called a 2 norm, it's called the 2 norm because of these complementary exponents. You square the polynomial inside the integral, and you take the square root of the result. All right, this is why it is called the 2 norm. You can come up with a version that's exactly the same idea, that's called the 3 norm. The polynomial under the integral would be cubed, and now you have to be a little bit careful. It has to be in absolute values to make sure that the magnitude is positive, but the idea is the same. And then you would take the cube root of the result. All right? So this is why it's called the 2 norm. This is the natural sort of extension of the usual way of measuring distances that we're used to, what we call the Euclidean norm. Right? The Euclidean norm on, say, R2 is the square root of x squared plus y squared. Right? And so you square the things under the square root, and you add them together. And that's all we're doing down here in this formula. We're squaring something, and we are adding stuff up. It's fancy adding because it's integration, but we're still doing, at the most basic level, we're doing the same thing. And then ultimately you take a square root as well. Okay, so this is the first big thing that we need to address. There is a way of measuring magnitudes of polynomials. All right, so a quick example. We could take the magnitude of the polynomial that is equal to x. This is, again, going to be the square root of x inner product x. This is the integral from 0 to 1 of x times x dx, all raised to the 1/2 power. This is going to be 1/3 x cubed from 0 to 1, raised to the 1/2 power. And so this is 1 over the square root of 3. All right, another example. We can calculate the magnitude of the constant function 1. This is the integral from 0 to 1 of 1 squared dx, raised to the 1/2 power. So this is basically the integral of just 1. This is x evaluated from 0 to 1, raised to the 1/2 power. So this is 1, which you would really hope that the magnitude of the vector that is constantly equal to 1 would be 1, and it turns out to be the case. So that's nice. That's reassuring. All right, so this leads me to the point that I wanted to make. We can now answer this question here. All right, so what we're going to do is say that because the cosine theorem is true in Rn, we are going to use it to define what has to make sense for the angle between vectors in P2. All right, so we're going to make a definition. We define the angle between P and Q, which are in P2 of 0, 1, via the formula that worked in Rn, so we are going to say that it should work here via the following. The cosine of the angle between them should be equal to their inner product divided by the product of their magnitudes. In other words, if we solve for theta here, theta would be the inverse cosine of this horrible looking formula. All right, so as an example, what is the angle between 1 and x? All right, well, we saw before that the inner product of x and 1 was equal to, right there, 1/2. And we just calculated their norms. Oh, right, these should be 2 norms, since we're specifically using the 2 norm. This is equal to 1, and the norm of, x was 1 over the square root of 3. All right, so the cosine of the angle between these two polynomials should be equal to this by our definition. And this is 1/2 over 1 over root 3 times 1. In other words, this is root 3 over 2. And the cosine of this angle being root 3 over 2 tells you that theta has to be something very specific, right? So this is going to be where x is bigger, the angle where x is bigger and y is smaller. That's going to be pi over 6. All right, so the angle between 1 and x, in this very bizarre way of defining an angle, is pi over 6, 30 degrees, if you prefer that. All right, and if you look at a picture of what is happening here, right, you can draw x, looks like that, and the constant function 1 looks like this. And what we're saying is that in this weird way of measuring angles, the angle between these two functions should be pi over 6. Strange, but there it is. So the next thing I want to do is address this other concern that we have. This question. Can we find polynomials which are orthogonal?